Right, please. Optical isomerism. This is a phenomenon. This is a phenomenon. This is a phenomenon whereby two structural isomers, it's a phenomenon whereby two structural isomers with the same physical and chemical properties, but differ in the direction of rotation of plane polarized light. But differ in the direction of rotation of plane polarized light. But differ in direction of what? Rotation of plane polarized light. Like I told you, we have optical isomers. Optical isomers have the same physical and chemical properties. Okay, we have said that in the previous classes. They have the same physical and chemical properties, but they tend to rotate what? They rotate the plane of what? Polarized light in different directions. Rotate plane of polarized light in different directions. We have said this. They differ, they have the same physical and chemical properties, but they tend to rotate the plane of polarized lights in different direction. Now, right, what are optical isomers? What do we call optical isomers? What are optical isomers? What are optical isomers? Okay, let's write. Optical isomers are structural isomers. Optical isomers, when I say isomerism, that would be a phenomenon. If I ask you define optical isomers, right? Optical isomers are structural isomers. They are structural isomers with the same physical and chemical properties. But rotate plane polarized light in different directions. We have discussed this before. We have said that what now? The plane of polarized light can be rotated either what? Clockwise or anti-clockwise. Or we say what? It can rotate the plane of polarized light in the positive direction or in the negative direction. So if you have the plane of polarized light rotating light to the right or rotating light to the what? To the left, it means we're going to have two types of optical what? Isomers based on the direction in which the plane of polarization of light is rotated. How is the plane of polarization of light rotated? How is it turned? That will determine the kind of optical isomer that is. But optical isomers are what? They are structural. They are what? Structural isomers. They are structural isomers. Like I said, with the same chemical and physical properties, but rotates plane polarized light in different directions. That is important to note. It's very important you note what we are discussing, what we are talking about. It's very important you note that. Let's go, please. Let's go. An optical isomer, optical isomers, right? Optical isomers must have an asymmetric center, must have an asymmetric center or a chiral center. Now, what do we have that qualifies as an optical isomer? Any molecule or compound that with an asymmetric center or a chiral what center. Don't forget what is called asymmetric. Double M, please. Double M. Asymmetric, that means that what? It's not symmetrical. Okay? It's not symmetrical. If it's symmetrical, you will not be having what? The different mirror images. If it's symmetrical, they will overlap, they will superimpose if it's symmetrical. So if you want to qualify as an optical isomer, they say you must have an asymmetric center or a chiral center. It's a must you have this. What do you call a chiral or asymmetric center? I've told you in the last class that a chiral center is a center like this carbon now. If this carbon is a chiral center, it must have four different molecules attached or surrounding it. Four entirely different molecules must surround this compound. Four different molecules must surround this compound. Okay, four different groups must surround it. This is a bromine, this is an alkyl, this is hydrogen, this is what? Hydroxy group. You must have four different centers surrounding it. Okay, and that will we'll call that one a what? A chiral center. You must have four different things attached to it. This can be propyl, it can be ethyl, C2H5. It can be anything, but not the same thing as this. If you have this, if you have C and you have what? You have H, you have the same H attached here, and you have, let's say, CH3 here attached, and you have what? CH3 attached here. This carbon is not an asymmetric carbon, and it's not a chiral center carbon, because this and this are the same. This and this are the same. So a chiral molecule, this is what? This is an achira. This will be called achira. To be called an achira center carbon. This is a chiral center because what is surrounding this carbon, they are all what? They are all different. They are all different. All these guys are all different. So for you to have an optical isomer, you must have a chiral center. Let's write please. Let's write asymmetric or asymmetric or chiral center. An asymmetric or chiral center. An asymmetric or chiral center is an atom. Is an atom bonded to four different atoms. Watch that, of different groups. We say what? An atom bonded to four, watch that, four different, not just anyhow group, four different groups. An atom bonded to four different groups. That atom will be what? Will be called an achira center. That atom will be called an achira center. That carbon atom will be an achira atom. That is, the atom has, just watch it. You have an atom, watch that, an atom bonded to four different groups will be called a chiral, or an asymmetric center. Chiral or asymmetric center for any molecule or for any substance to be optical isomer of another one. For you to have optical isomers, you must have a chiral. You must have a chiral or an asymmetric center. And I say that what a chiral or asymmetric center is an atom bonded to four different groups. Atom bonded to four different groups. Let's write, please. This atom has different groups surrounding it. This atom has different groups surrounding it. This atom has different groups surrounding it. Full stop. Full stop. Continue. The atom with an asymmetric center, the atom with an asymmetric center is usually a carbon atom. Is usually a carbon atom. Take note of that. In other words, we have said that what? Carbon has that tetravalent nature. So that means that what? If you're going to have an asymmetric center or a chiral center, you should usually have a carbon as the central atom. Why? Because carbon has that tetravalent nature. That is, carbon has that tendency of having 4 other atoms surrounding it. Carbon has that tendency of having 4 other atoms surrounding it. So carbon is usually the asymmetric what? Or chiral what? Chiral center. Let's write please. Examples of molecules with chiral center carbon atom include, look at this, you have C, you have C2H5, you have OH, we have OH, we have hydrogen, we have CH3. Then this carbon, the asterisk carbon, that asterisk carbon is a what? A chiral center carbon atom. That's a chiral or asymmetric carbon atom. Chiral center carbon atom. Chiral center carbon atom. Chiral center carbon atom. That's what you are seeing there. Chiral center carbon atom. Now tell me, can someone tell me, is there a chiral center in this molecule? If you have CH3, CH, CH2, CH3, then we have Cl. Now let's first check. Look at this molecule very well and tell me if it can have, if it's an optical isomer, if it can rotate plane of polarized what? Light. Does it have, you have to first check, does it have a chiral center? That's the first question. Does it have a chiral center carbon atom? That's one. If it has a chiral center carbon atom, then which of the carbon atoms here is that chiral center carbon atom? Let me label them. Carbon atom 1, carbon 2, carbon 3, carbon 4. If you look at this molecule very well, the second carbon atom is a chiral center carbon atom because you can see that what is attached. Let's see this way. Let's see this way. Let's see this carbon. This carbon 1, see the carbon 1 is attached to hydrogen, hydrogen, hydrogen. That's this carbon, carbon 1, this carbon 1, this carbon 1. Then it's also attached to carbon 2, this carbon 2, this carbon 2, this carbon 2 here. You can see my hand. So that carbon 2 also, what you observe, is attached to hydrogen, is attached to chlorine, and is attached to another carbon 3. This carbon 2 attached to carbon 3. Carbon 3 is attached to who? This carbon 3. This carbon 3 is attached to hydrogen, attached to 2 hydrogen, and is now attached to carbon 4 again. This carbon 4. The carbon 4 is attached to what? Hydrogen, hydrogen, and hydrogen. So if you look at it very well, which carbon atom has 4 different groups surrounding it? This carbon, yes, it has 4 groups surrounding it, but they are not different. They are 3 are hydrogen. See them? 3 are hydrogen, so they are not different. So this is not, carbon 1 is not a chiral center. Carbon 2 has how many groups? Let's see. This group, look at it. This as a whole, watch. This as a whole is attached to this carbon. It's attached to this carbon, which is what? C2H5. C2H5. This is attached to this carbon. This O methyl also, this O methyl is attached to this carbon, and this chlorine is also attached to that carbon. So you have 1, 2, 3, 4 groups attached to that carbon atom. And in that case, we call that carbon atom a chiral center. So carbon 2, this carbon 2 I have steric here, this carbon 2 asterisk here is a chiral carbon atom. Carbon 2 is a chiral carbon atom, or is an asymmetric center. Now, assuming what you have on this side, is H, on this side is H, on this side is H, on this side is H. This carbon here will be what? Symmetrical. That means what you have on the left is what you have on the right. It will be called a symmetrical molecule. Let's assume we don't even know what you are doing for now. Let's assume that we are laymen in chemistry. If you draw a line like this, what you have down, what you have up are the same. That means this molecule is symmetrical about this carbon atom. Symmetric means that what? Okay, let's see what is called symmetric. If you look at what? A circle in a mirror, what you will see is the same circle. There's no difference. If you cut a circle like this, I'm trying to explain the meaning of symmetric. If you cut a circle like this, what you see on this side, just watch. What you see on this side, what you see on this side here and on this side here, they are both the same thing. You don't see different thing. What you see on this side here, this side that I'm pointing to, this side, and what you see on this side, they are both the same thing. So if you look at the circle through a mirror, okay, we'll soon get to that one. We'll get to that one. I'll explain better when we get to that one. So in summary, this is a chiral center molecule. This is a chiral center molecule. Chiral center molecule means it has a chiral center carbon atom, which means it has a carbon atom surrounded by 4 different groups entirely. Okay, that's what a chiral center atom. Let's go. So I've given you 2 examples. This one, and this second example. So draw the 2 down. So I asked you in this question here, I said, is this molecule a chiral center molecule? Yes. Can this molecule form an optical isomer? Yes. Which of the carbon atom is a chiral center carbon atom here? We said carbon number what? Number 2, which means it's a chiral center molecule. Chiral center molecule. Thank you very much. Let's go to the next example. Look at this molecule. Tell me if it has a chiral center carbon atom. Look at it. We have CH3, we have CH3, we have CH, we have CH3, we have CH2, we have CH, we have CH3, we have CH3 also. Now tell me, this molecule, does it have a chiral center carbon atom? Label the carbon atoms. Let's label all the carbon atoms. 1, 2, 3, 4, 5, 6, and 7. So we have 7 carbon atoms on the board. So which of these carbon atoms can be a chiral center? Carbon number 4 here has, look at it now, it has hydrogen here, it has CH3 here, it has CH3 here, and it has these other molecules on this side. These 2 are the same already. They are the same. They are not different. So that means that what? It cannot be a chiral center molecule. It can be a chiral center molecule. Why? Because there's CH3 here and there's CH3 here. So it's not chiral, it's achira. This is achira. It's not a chiral center molecule. So let's go. So there is no chiral center carbon atom here. The molecule is what? Asymmetric. Let's go, please. Asymmetric center in the molecule. Asymmetric center in the molecule is a cause of chirality in the molecules. Asymmetric center in a molecule is a cause of chirality in molecules. Is a cause of chirality. Is a cause of, see the board, chirality. Is a cause of chirality in the molecules. Full stop. Full stop. Full stop. A chiral center has a non-superimposable mirror image. A chiral center has a non-superimposable mirror image. Has a non-superimposable mirror what? Image. That means that what? The mirror images or the mirror image of that molecule cannot be superimposed on each other. You cannot overlap them on each other. If you look at a circle, if you look at it, see the board, look at the board. If this is a mirror, you have a circle here, you have a circle here. Now, this circle here is a mirror image of this circle. If this is a mirror, just watch. This is a mirror image of this one, and they are exactly the same thing. You can superimpose them because it's a symmetric molecule. It's a symmetric object. It's symmetrical. So you can overlap on each other. You can overlap on each other. It can be superimposed on each other. But chirality in molecule will result in non-superimposable what? Mirror images. That means the images seen in the mirror will not be what? Overlappable. They will not be able to overlap on each other. You cannot overlap them on each other. That's the meaning of what? Non-superimposable. Non-superimposable. Let's go, please. Let's go. That is, its mirror image is not the same. That is, right. I said what? I said a chiral center. A chiral center has a non-superimposable what? Mirror image. That means its mirror image cannot be overlapped on the real object. You cannot overlap the image and the object on each other. They will not fit perfectly into each other. They will not fit perfectly into each other. Okay. When you use use your left hand to look at put your left hand in the mirror. It will do what? It will turn to your right hand. So the two of them are not superimposable again. So let's go. That is, its mirror image is not the same as the real object. That is, its mirror image is not the same as the real object. That is, its mirror image is not the same as the real what? Object. That means you cannot really what? You can differentiate the image and the object. That's the meaning. You can say, okay, this is the object, this is the image, because they are not the same thing. They are not the same thing. Okay. Let's go on, please. Let's go. Paragraph. A compound with one asymmetric or chiral center. Compound with one asymmetric or chiral center. A compound with one asymmetric or chiral center exists as two optical isomers. Exists as two optical isomers. Exists as two optical isomers. Once there is one asymmetric or chiral center, it exists as what? Two optical isomers. Right, exists as two optical isomers. Exists as two optical isomers that are mirror images of one another. That are mirror images of one another. That are mirror images of one another. A compound with one asymmetrical or chiral center exists as two optical isomers. Exists as two optical isomers that are mirror images of one another. That are mirror images of one another. Full stop. Their mirror images are not superimposable. Full stop. Full stop. This is analogous. This is analogous or compared to the images of left and right hands. Left and right hands. Analogous to the images of left hand and right hand. Of left hand and right hand. Analogous to the images of left hand and right hands. What did I say? Look at the board. Look at the board. I said that what? If you look at your what? Your hand. Your hand. See your hand. I wish I can draw. We see your hand. This is your hand here. This is your thumb. This is your thumb. This is finger. This is finger. This is finger. This is smaller finger. Okay. If you look at this guy in the mirror, what you will see is your what? Is your right hand. You will see the smaller finger first. You will see what? Something like this. You see the smaller finger first. You see what? The smaller one, the central one. You'll now be seeing the thumb on this side. You'll be seeing the thumb on this side. Just pardon my image, okay? I'm not an artist. What I'm saying is that what now? You cannot put this, watch, this is what? This is thumb here. This is thumb here, but this is thumb here. This is your thumb here. That's your thumb here. This is your what? This is smallest finger here. This is smallest finger here for this one. See thumb here. See where thumb is here. So if you now put, watch, just watch. Carry this thing like this. Carry this like this. Like this. So you have place this thing like this on this. Place this on this. You will see that what? The thumb will fall on the smallest finger. Why the what? The smallest finger here will fall on the thumb. They will not be what? They will not be they cannot overlap each other. They cannot be on each other. We say the two hands are mirror images of each other and they are not superimposable, which means you cannot overlap them on each other. It's not possible. You cannot put this, you can't put this on this, and you cannot put this on this also. They are non-superimposable, and these two are called optical what? Optical isomers. They are called optical isomers. Images from plane mirrors are laterally what? Inverted. Like left becomes right, right becomes left. They are not inverted, they are only laterally inverted, which means they have sideway inversion. They have sideway inversion. So now let's go on. As I said, look at the board. Any molecule which has one asymmetric or chiral center, we have two optical isomers, which are analogous to the left and right hand, our left and right hand. Let's go, please. Let's go to the next thing, right? Molecules, just watch this. These are terms they will ask you to define. They can ask you to define asymmetric, see the board, asymmetric or chiral center. Asymmetric or chiral center, or they will say define chirality. They can ask you to define what they call optical isomer. Optical isomers. What are optical isomers? Okay, they can ask you to define these two. They can ask you to identify the molecules. They are what? That the molecules are, they can turn the plane of polarized light. They can rotate the plane of polarized light. They can ask you to identify which molecule, can say which molecule below, which of the molecules below can rotate the plane of polarized light. Polarized light. They can ask you, what will be your answer? You will look for molecules which has a chiral center. Which has a chiral center. They can ask you, which of the molecules are mirror? I mean, they are non-superimposable mirror images of one another. Which of the following is a non-superimposable images of one another? They can ask you that also. They can ask you that also. These are things you have to what? You have to learn. They are things you have to learn, okay, to define, to explain. Let's write. Paragraph. Molecules that are non-superimposable mirror images. Molecules that are non-superimposable mirror images of each other. Molecules that are non-superimposable mirror images of each other are called enantiomer. Enantiomers. They are called what? Enantiomers. From the word enantio, like this, see the spelling? Enantio. See the word? Enantio. The word enantio with N. The word enantio means what? Opposite. This guy means opposite. Molecules that are mirror images of each other. That is, molecules are opposite of each other. Molecules which are opposite of each other, they are called enantiomer. Okay, that's what enantiomers. So we say what? Molecules which are non-superimposable mirror images of each other are called what? Enantiomers. They are called enantiomers. So they ask you, define enantiomers. They can say define enantiomers. So if two molecules are mirror images of one another, we call them what? Enantiomers. The two of them are enantiomers. They are optical isomers. Enantiomers are optical isomers. They are mirror images of what? Of each other. Sorry, they are non-superimposable mirror images. Yeah, you must put the word non-superimposable because if they are superimposable, that means there is no chiral center. There is no chiral carbon atom. Molecules which are non-superimposable mirror images of each other are called what? Enantiomers. They are enantiomers. Let's go, please. Let's go. Full stop. Such molecules are chiral. Such molecules are chiral or or they are chiral or asymmetrical. Such molecules are chiral or asymmetrical. Such molecules are chiral or asymmetrical. Full stop. Full stop. Paragraph. A molecule that has a superimposable mirror image, right? A molecule that has a in this case, superimposable molecules with what? Superimposable mirror images of each other is chiral. They can ask you, define an chiral molecule. What do you call chiral? Chiral molecules are molecules with superimposable images. Like what? Look at a circle in a mirror. You will see a circle. You can put the circles on each other because it's symmetrical. Right? It's chiral. See the word? Chiral. And the molecules are symmetrical. E.g., look at the board. I want you guys, can you guys do me a favor? I want you to draw this molecule on paper. Draw this on paper for me. Tear a paper and draw this for me the way you see it on paper. Draw it the way I drew it here on paper, please. Draw this thing for me on paper the way I drew it. Draw for me on paper, please, and follow my instruction. The same way I have drawn it, draw it for me on paper. Draw this thing for me on paper, please. Please, draw this for me on paper. Draw this for me on paper, please. Draw it for me on paper, please. Yeah, this is a mirror. Now, have you guys drawn this on paper for me? Oh yeah, good. Oh yeah, draw this scene exactly what I drew on this board. Draw it for me exactly on paper. Draw it exactly on paper, the way it is, the way I put the atoms. You know that what now? You cannot really draw this thing like this. You can't really draw this thing like this. It's not really correct. It's not correct. You know that. It's not correct. It's not correct. It's not really correct. So you can see that what? The bond angle here is looking like it's 90 degrees, but the bond angle is not 90 degrees. So it's not easy way to draw it. Now, yeah, turn the back of that paper. Turn it. Turn the back. Turn the back of that paper. Yeah, draw exactly what you see on that paper down. You know that if you turn it, you will be seeing RB like this. You'll be seeing RB like this, but don't draw IB. Just still draw your BR. If you see RB, still draw BR. But draw it. Where is hydrogen now? Where is CH3 now? Where is C2H5 now? Draw them. What you see on that paper, draw it out for me. Let me now draw my own and tell me if you are correct. You tell me. This is a mirror. This is my mirror. This is my mirror. That's the mirror. So what you will see exactly is something like this. Carbon is still carbon. You know that carbon will look like this. Abi, at the back of the paper. At the back, it will look like this. Am I correct? This is but you don't draw. You still draw your normal carbon. Exactly. I don't draw like this. Still draw your normal carbon, your normal bromine, your normal ethyl, your normal methyl. So let's go. Bromine is still on top. Even though it appears like RB, but don't mind RB. You will see this guy, CH. You see C2H5 will be seen on the right hand side now, no longer on the left hand. It's no longer here again. It's now on the right hand side. If you look at your paper very well, your hydrogen will be here now. Will be here. Instead of pointing, see the word. See how this hydrogen points here. See how it points here. It goes to point like this here now. See how this one points here. See how your methyl here. See how methyl point. It point like this. It's going to point like this here now, opposite. Now, see how this guy points here. See how methyl points. See how it points? It's going to point what? It's going to point the other way now, like this. Now, to point this way now. This is your what? Methyl. But what you'll be seeing will be what? Will be H3C. You'll be seeing H3C. I want you to pay attention, please. If you look at it very well, you first see, you see what you'll be seeing will be what? H3C. No longer CH3. You'll be seeing H3C. You'll be seeing what? H3C. Take note of that. Take note of that. Take note of that. You'll be seeing H3C. Even this one, you'll be seeing what? You'll be seeing what? H5, then C2. You'll be seeing H5, then what? C2. It will reverse. CH5, C2. Abi? But the C must be attached to the bond. Please take note of that. The C must be attached to the bond. The C to the bond. Is that okay now? So this is what you will see. What I want you to observe, if you have drawn this thing now, what I want you to observe is simple. Look at it very well. What I want you to observe, just look at it very well and see what I want you to observe. Bromine is bromine. Bromine is bromine. Now, this edge, see this edge, see this edge, see how it's pointing here, see the bond, see the bond, see the bond, see this edge now, the bond direction has changed. It has what? It has rotated, or it has what? What's it called? How will I put it? Direction has what? Has changed. It has become left has become right, right has become left. See this guy also, see this guy also, which was like this. See how it is here now? It has changed to this. Now, see C2H5, it become H5C2. C attached to, the bond attached to carbon. This is CH3. See how the bond looks like. See how it goes. This is the bond. See the bond there now, it's like this. So let's see. Let's see. That is how to draw. We say what? Look at the board. We say what? This molecule is a mirror image of this molecule. Why? Because if you carry this thing like this, and put on this thing like this, they will not superimpose perfectly. You will be seeing this H. H will be overlapping with what? H5C2. C2H5 overlap on H. They will not even overlap completely. CH3 overlap on H3C. You will not have an overlap. You will not have a superimposition on the two molecules. And the two of them are called what? Enantiomers. These two are called enantiomers. They are called enantiomers. They are called enantiomers. What are enantiomers? Molecules which are non-superimposable mirror images of each other are called what? Enantiomers. Are called what? Enantiomers. I said enantio means opposite, or enantion as you like it, means opposite. They are opposite of each other. You can see all their bonds. All their bonds are reversed. All their bonds are reversed. They are opposite. All the bonds are already opposite of each other. Thank you very much. Thank you very much. And why is this molecule able to do this? Because the carbon atom is chiral. The carbon atom is chiral. That central carbon atom is chiral. What makes it a chiral carbon atom? Because four different groups are attached, are surrounding it. Four different groups are surrounding it. Let's go. Let's go. The following molecule has a superimposable mirror image. Has a superimposable mirror image and is an Akira molecule. And is an Akira molecule. Is an Akira molecule. It is an Akira molecule. It is an Akira molecule. Look at this. Tell me what makes this thing to be Akira. What makes this to be Akira? You will tell me now when I'm done drawing. What makes it Akira? You will tell me. What makes this guy Akira? It has two similar grooves. It has two similar grooves. For this carbon to be a chiral carbon, it must have what? Only one. It must have what? Four different groups around it. So the carbon is Akira. The carbon is Akira. Is Akira or symmetrical. And the mirror images will overlap each other. Mirror images will superimpose. Mirror images will superimpose. Mirror images will superimpose. Let's write this. Let's write chiral center molecules and plane polarized light. That's subheading. Chiral center molecule chiral center molecule, and plane polarized light, What do we say a chiral center molecule can do to plane polarized light? We said a chiral center molecule can form optical what? Isomers. And the optical isomers are called enantiomers. They are mirror images which are non-superimposable on each other. And because of this, we said optical isomer can rotate what? Plane polarized light. And because there are two things are mirror images of each other. We have your right hand and its mirror image is your left hand. This is a mirror. Your right hand mirrors this an image of your left hand. That's what we'll see in the mirror. The two of them, if these are enantiomers, the two of them will rotate plane polarized light in different directions. We rotate plane polarized light in different directions. And as a result of that, that means that what? We have two types of rotation because we have the enantiomers, okay? One of the enantiomers will rotate light, plane polarized light to the left. One rotates it to the what? To the right. So let's write this down fast. A plane polarized light is one that oscillates in a single plane. Is one that oscillates in a single plane. Full stop. It can be produced. That's what plane polarized light. I want to produce it now because the normal light we see every day is not plane polarized. It moves in different directions. The light scatters. Plane polarized light is not scattered. It's only what? Unidirectional. It moves in one direction, okay? Good. Let's go. I said what? It can be produced by passing normal light. Like light from the bulb, light from your bulb or from the sun, light from the bulb or the sun. This light from this bulb and this sun and the sun, of course, they are not polarized, they are scattered. Right, can be produced by passing normal light, in brackets, light from the sun or the bulb through a polarizer, in brackets. Examples of polarizers. Give me examples of polarizers. Examples of polarizers include your what? Your nickel prism. Also your what? Your polarized lens. These are examples of polarizers. Polarized lens. These are examples of polarizers. Polarized lens. So if you pass, look at the board. Don't make mistake. We said plain polarized light means light that oscillates, that moves in just one direction. Okay? And I said what? How do you produce a plain polarized light? I said you should pass what? You should pass your light, the light we see every day. Our bulb light, pass it through a what? A polarizer. And I said, what are the examples of what you can pass the light through? You can pass the light through your nickel prism. Nickel, not nickel. Nickel prism. And you can also pass it through a polarized lens. And that can make an unpolarized light. It can make an unpolarized light to become polarized, which means it can make light that scatters to become polarized. That is, move in just one direction and perpendicular to that direction anyway. Good. This is not physics class, this is chemistry. So let's go on. Let's go on. Let's see how this can be achieved. Let's write. Let's write. A chiral compound. A chiral compound. We have said it. We know what a chiral compound is. A chiral compound can form enantiomers. Good. A chiral compound rotates. A chiral compound rotates. If they ask you which of the following can rotate the plane of polarization of plane polarized light, look for a chiral compound. How do you get a chiral compound? It will have a central carbon atom surrounded by 4 different groups, and this will form enantiomers. Enantiomers are what? Are what's it called? Molecules which are mirror images, which are non-superimposable mirror images of one another. So let's write. A chiral compound rotates. A chiral compound rotates. The plane of polarization rotates. The plane of polarization rotates. The plane of polarization of plane polarized light. Rotates the plane of polarization of plane polarized light. Of plane polarized light. Full stop. Full stop. Full stop. A chiral compound. A chiral compound can rotate the plane of polarization. A chiral compound can rotate the plane of polarization clockwise or anti-clockwise. Can rotate plane of polarization clockwise or anti-clockwise. Can rotate it clockwise or anti-clockwise. Now let's see the board. Look at it. See the board. This is light source. This is what? Your light source. Light source. I don't know what the source is. This is your what? This is how the normal light, the light that comes from this source, this is how it's going. See the light. See how the light is going. See how it's going. It can go like this. It can go like this. It can go like this. It's scattered. It goes in all directions. It's scattered. It goes in all manners of directions. That's what? Your normal lights. Normal lights. What you see normally. Normal lights. Either from the sun or your lap. It scatters. That's why if you on your bulb in the room, the light disperses in the whole house, in the whole room. If the light is not dispersing, that means that what? Some corners of the road, there will be no light there. So the light scatters. You can see how it's scattered. You can see the scattering of the light. Light is scattered. But when the light is now meant to just face a particular direction, you see the light becomes polarized. So I can pass this thing through a polarizer. This is a polarizer. A polarizer. This is a polarizer. Okay. When the light passes through a polarizer, what I see is now light that moves in just one direction. That moves in just one direction, vertically only. Moving vertically only. The light is moving vertically only. This is called plane. This is called plane polarized light. This is called plane polarized light. If you now pass this light through a chiral compound, this is a tube. This is a tube containing a chiral compound. Okay, what do we see? This light, which was like this, once it enters this tube, we have this is a sample tube containing a chiral compound. Look at it. It's containing a chiral compound. Just look at it. When this, see the board, light source, that's it, where the light is coming from. This the light that comes from it. This is the light that comes from it. Is normal light. That's unpolarized. This is unpolarized. 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 This is now what? Polarizer. Which want to make, this one want to make the what? The light to become polarized. This is now polarized light. This is plain polarized light. So the plain polarized light is now entering here. As it enters here, what happens? It starts turning. See, it starts to turn. See, it's turning. You can see that it's what? It's turning. It's turning clockwise. It's going like this. It's going like this. You can see how it's going. See how it's going? It's going like this. It's going clockwise. It's turning. It's turning. So it's turning. It's still turning. You can see it's turning. What is making it to rotate here is the, what's it called? I said containing what here? Containing a chiral compound. Also, what's making it to turn? What makes it to rotate is this chiral compound inside this tube. So at the end of the day, what do I see? We see this guy. We see that what? This light has turned like this. Which means what was vertical like this? See what was vertical? It has turned to this direction. It has turned clockwise. So let's draw that down, please. Draw it down. So you are seeing how you are looking at how what's it called? A chiral compound can rotate plane of polarized what? Plane of polarization of plane polarized light. You can see what I first did. I have my normal light here. I put it through a polarizer. It got polarized and it comes out here as vertical line, vertical direction, okay? Plane polarized light, you can see. Then it enters the what? The tube that contains the chiral molecule. And we know that what? A chiral compound will always rotate the plane of polarization of plane polarized light. That's what it does. Once you are asymmetrical, once you are achiral, once you have a carbon atom which has 4 different groups attached to it, you are going to form enantiomers. Enantiomers are molecules which are non-superimposable mirror images of each other. Their mirror images cannot be what? Superimposed on each other. That's that on that. Let's go on. If you are drawing, I go to the next topic. Let's write. Optically, that's paragraph. Optically active compounds. Optically active compounds are compounds. They can ask you to define it. Optically active compounds are compounds that rotate plane of polarization, are compounds that rotate plane of polarization of plane polarized light. Optically active compounds are compounds that rotate the plane of polarization of plane polarized light, of plane polarized light. Just watch that. See the board. Define an optically active compound. You can see. Define an optically active compound. Define it. What do you call optically active compounds? They are compounds that can rotate plane of polarization of plane polarized what? Light. Tell me, are chiral compounds optically active? Are chiral compounds optically active? That's a question. A very big question for JUPEB. Are chiral compounds optically active? Are chiral compounds optically active? Yes. Yes. Why? Why are chiral compounds optically active? That's another question. Why? You say because chiral compounds are optically active because they can rotate the plane of polarization of plane polarized light. They can rotate the plane of polarization of plane polarized what? Light, either clockwise or anti-clockwise. Right, please. Right, right. Chiral compounds Chiral compounds are optically active compounds. Chiral compounds are optically active compounds. Why are chiral? Why are chiral? Watch that. Why are chiral compound? A chiral compound are not optically active. They are optically inactive. They are optically they are optically they are optically inactive. They are optically inactive. They are optically inactive. Chiral compounds are optically inactive. Why? Because they are chiral. Why are they chiral? They have no carbon atom that has 4 different groups surrounding them. Why are they optically inactive? They cannot rotate the plane of polarized light. Let's go. Let's go. Next paragraph. Next paragraph. An optically active compound. An optically active compound. An optically active compound that rotates the plane of polarization. That rotates the plane of polarization of plane polarized light. That rotates the plane of polarization of plane polarized light clockwise or right. Clockwise, clockwise or right. If you rotate the plane of polarized light clockwisely or to the right, right, is said to be dextro-rotatory. 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 Hope the spelling is correct. Dextro-rotatory. I said what? An optically active compound that rotates the plane of polarization of plane polarized light clockwise or right. If you rotate it to the clockwise direction or to the right, it's said to be dextro-rotatory. Dextro-rotatory. Indicated by the prefix positive or D. Indicated by the prefix positive or D. So we say what? To the right or positive direction or dextro-rotatory. So if you see D, if you see an enantiomer and they say they put enantiomer and they put D in brackets, that means that what? Is dextro-rotatory. That means that enantiomer will rotate light to the right, or you can say right or say clockwise or say in the positive direction. Let's write. An optically active compound. An optically active compound. An optically active compound that rotates the plane of polarization. That rotates the plane of polarization of plane polarized light. Of plane polarized light. Counterclockwisely. Counterclockwisely or left. Counterclockwisely or to the left is said to be levo rotatory. Levo rotatory. Levo rotatory. is said to be level rotatory, indicated by minus, indicated by minus or L or capital L. Capital L. So you now determine the enantiomer, the optically active molecule, is it rotating light to the left or to the right? You have to decide based on the question. Let's write positive and negative. Right, like this, right, like this. Positive and negative. Quote it like this. Or D and L. Quote them, or D and L. Or D and L symbols indicate the direction. Indicate the direction in which an optically active molecule indicates the direction in which an optically active molecule rotates the plane of polarization, indicates the plane of polarization, indicates the plane of polarization of plane polarized light, of plane polarized light, of plane polarized lights, of plane polarized lights. Full stop. So D and L, or plus and minus, tells you the direction in which the light is rotated. Let's write. Paragraph. Another thing they can ask you to define is what? Racemic mixture or racemic modification. They can ask you to define racemic mixture or racemic what? Modification. One of the two. That's another question they can ask you. Racemic mixture or racemic what? Modification. Let's write. An equimolar mixture. Of two enantiomers. Just take note of that. They ask to define it. An equimolar mixture of two enantiomers is known as racemic modification. Is known as racemic, some will say racemic. Racemic modification, or racemic mixture. When you have equimolar mixture, that's what? Equal molar, equal amount, equal concentration, equimolar mixture of two enantiomers. They are equal, they are in the same proportion, 50-50% each. Equimolar mixture of two enantiomers. Light is known as what? Racemic modification or racemic what? Mixture. Full stop. A racemic mixture, right, paragraph. A racemic mixture is optically inactive. A racemic mixture, right, please. Racemic mixture is optically inactive. Why? Why is a racemic mixture optically inactive? Can anybody tell me? Why is it optically inactive? It has equal amount, equal mixture, equal molarity, equimolar, equal amount of the D and the what and the L. It has equal mixture of what will rotate to the left and what will rotate to the right. It has equal mixture. Yeah, look at the board, please. Look at the board. If you have a racemic mixture, that means what? We say what? Equimolar mixture of what? Of two enantiomers. If one rotates to the right, watch you see this thing. Look at this light. See the board. Look at the board. If you pass this thing through, if you pass it through what? A racemic mixture. One will do what? See the board. One will do what? Turn it like this. Watch. One will turn it like this. One will do what? See, one has turned it what? Clockwise. Either D has turned it clockwise. If D turns it clockwise, that's what D in that mixture. Now, the other part of the what? Of the racemic mixture, we turn it back what? We turn this thing back like this. See the body? One turns it, sorry, hold on. Just hold on. One turns this thing like this. So it becomes this. This, see the what? This becomes this. While the other one turns this thing back like this. It turns it back like this, and it comes back to this again. So as one rotates to the left, the other will do what? Rotates it to the right. That means this thing will not rotate on overall. Because as one turns it like this, the other one return it back to this. As this one turns it like this one turns it back like this. It becomes this one back. If this becomes this, then this becomes this again. That means this thing does not change. Its rotation is not what? Successful. Let's write. This is because the rotation caused by one enantiomer. This is because the rotation caused by one of the enantiomers is exactly cancelled. The rotation caused by one of the enantiomers is exactly cancelled. Is exactly cancelled by the rotation produced by the other enantiomer. Is exactly cancelled by the rotation produced by the other enantiomers. So in this place now, they can ask you to define, what's it called? They can say you should define racemic mixture, and they can ask you, is racemic mixture optically active or inactive? Why is it optically inactive? If it's inactive, they can ask you. This is where we conclude. We have this to do, which we'll do in questions. How to draw enantiomers. Put it down, please. How to draw enantiomers. I will do it as video and send it to you. I will do it as video alone and send to you. How to draw enantiomers. Then again, though we have two methods. We have the what? The perspective formula and the feature projection. There are two formulas, but we continue in the next class. Let's see the next one. The next one is what? Naming enantiomers. How to name enantiomers. Naming enantiomers. Using the what? By RS system. Which is called RS scan. By RS scan, C in gold, and V prelog. They will not ask you for the names. I'm only just telling you. So we have two things to do now. How to draw enantiomers and how to naming enantiomers using the RS system. That's RS scan, C in gold, and V prelog method of naming enantiomers.